access to 5 structures, even though there were only 4 directly tested. And when we looked at those, okay, we said the aniline should react faster than the toluene, which should react faster than the acetophenol, which should react faster than all the others. So this was really, really fast. And this was really, really slow. When we looked at the fast one, what positions were activated? Where was our most likely product? Para. The next one. Toluene. It was para as well. Next one. It was our meta. The next one. The last one, which you guys probably haven't solved yet, but it does come out. Oh, sorry, the middle one you didn't solve yet. It does come out to be meta. The nitro we solved was meta. Okay, so what we want to try and do is come up with an analysis that would allow us to quickly come to these same conclusions. Okay. For our reaction to go faster, what does that substituent have to do to the ring? It has to donate electrons. So the faster must be an electron donor. Slower needs to be an electron withdrawer. Let's just say that says withdrawer. It has to be a better electron donor than what to be faster?
Carbon.
Actually, no. Not a bad guess, but no, not carbon. Because we've got faster, which is positive, and we have slower, which is negative. What's dead in the middle? Neutral, or 0. What is our 0 point when looking at these reactions? Just a benzene ring. I like that. What's the atom? Our 0 point is looking at hydrogen. Everything is based off of hydrogen. So when I look at the toluene, I'm comparing hydrogen to carbon. Which one has more electrons to donate? Carbon, because it's bigger, more electrons. Which one has more electrons to donate in comparison from hydrogen to aniline? Nitrogen. Okay. If we compare nitrogen to carbon, nitrogen, because? Lone pair. Okay. If we then do the reversed, our 0 point, hydrogen down to the nitrogen in the protonated aniline. What's that? We're comparing hydrogen. That's what I actually said first, was that one. Hydrogen has more electrons, which means the nitrogen one needs to be going slower. Okay, where I think you might have been answering, Troy, was the logical conclusion, which would have been the acetophenone. I'm comparing hydrogen to what atom? Carbon. The atom immediately connected. Which one has more electrons? Doesn't carbon have more electrons? Isn't that what we said for the toluene? That oxygen electron withdrawals, that carbon actually has less electrons than a hydrogen atom. How do we have less electrons than a hydrogen atom? How many electrons does a hydrogen atom have? 1. How do we have less than 1? You become positive. What happens when we move to the protonated aniline? Same deal. We have a positive nitrogen. We move to the nitro? Positive nitrogen. So what we're doing is comparing that atom, whatever that atom is, as it's directly attached to the ring, and comparing it back to hydrogen and deciding, does it have more electrons or less electrons? If it has more, well, that speeds up the reaction. If it speeds up the reaction, we can then go through and look at all of our resonance contributors, and we notice that the para position ends up being dominant. Okay? As was astutely pointed out, we also have the ortho as a possibility there. Okay? It generates the same resonance. Why did we pick the para over the ortho? Sterics. So the para is predominant, but what if the para is blocked? And then I get the ortho. Okay? What if the para and the ortho are blocked?
You get nothing.
I get nothing. Okay? The reaction doesn't occur for the activated ones. What about the deactivated ones? If I take a look at that nitro compound and both meta positions are blocked, nothing happens. Okay? I can't react at the para or ortho positions because I end up generating very, very unstable intermediates. They're so unstable they can't form. Kind of make sense? Okay. So here's our big summary. Okay. What do we see at the top? X with electrons. Okay. In that case, we're saying X has more electrons than hydrogen. It's an electron donor. We could go through and evaluate a resonance contributor. When we look at that resonance contributor of it donating electrons, what result do we see? What did you say, Troy? I see a negative carbon. Where's that negative carbon located? At the ortho position on the ring. What did we say happened when we had an atom with more electrons? The para and the ortho positions were activated. Why would it be activated? It's a negative charge, and the ring has to act as a nucleophile. There it is. What happens if you continue to do resonance?
Moves it down to the para.
We'll notice that you can put that negative charge at the para position, activating it as well. What happens in the bottom case? X has less electrons than our hydrogen. The result is that the electrons leave the ring and go upwards. Where does the charge build? The ortho position. But if it builds the ortho position, shouldn't it react to the ortho position?
Isn't there going to be a positive charge?
What's the charge that builds at the ortho position?
It's not,
A positive.
it's not nucleophile at that point.
The ring must act as a nucleophile in the EAS reaction. If I put a positive charge there, it cannot act as a nucleophile. That position is now off the charts, impossible to react because there's no electrons. I can't react at the ortho position. What happens if I continue to do resonance?
It's going to push it down to the para.
I will see the positive charge build at the para position. So if I look at the situation where our atom X withdraws electron density, I see the ortho and para positions being completely unavailable for reactivity because they're positive. Well, I'm also seeing that the overall charge on the ring now is positive. Well, if it's positive, what should happen to the rate of the reaction? It should slow down. If I now force it to react, what position can possibly react? Only the meta, because the ortho and the para are unavailable due to the positive charges building at those positions. So we have two approaches to go through and predict the reactivity of our EAS reactions when we've added a substituent. That's going to change which of those pi bonds reacts and where our group ends up attaching. Okay? We can look at it by either drawing it out officially correctly, looking at the sigma structures and looking at the intermediate energies and how those change the individual products we get, or we could draw out the resonance from the starting aromatic ring and use that to help us predict. Okay? Both get us to the same answer. Looking at the intermediates is a more correct way of looking at it. Looking at the starting material is officially not correct. Okay? Both get you to the exact same answer. So in our last summary here, in the bottom case, because our ring is positive, okay, it cannot react. We need to come up with a fancy word for that. We can call it a deactivator. Where would it direct? Meta position. In the top case, my ring is negative, so it is now more likely to react. I can call the substituent a activator or and para-ortho directing. You will notice that you will hear people refer to activators, as ortho-para directing. That's not wrong. I prefer the statement para-ortho than ortho-para because para is more likely to react. So if you can get in the habit of saying para-ortho, you should be locking in at that para position a little bit faster and more efficiently. Okay? I can't remember if we throw in the monkey wrench yet. There's all our pretty structures. Okay, I did not throw in the monkey wrench yet, so let's go ahead and do it. So, new structure. Chlorobenzene, which could have just as easily been bromobenzene or iodobenzene. Okay. Spend 2 minutes, talk to the people around you, decide. Activator, deactivator, para-ortho.
The size.
What does the size have to do with it?
Can't do resonance with it.
Yes. Because it's so large, we don't get very good resonance overlap, which means those electrons cannot make it into the ring, which means no activation. Okay. However, there are electrons there, so they kind of contribute to the para-ortho positions being less or more reactive than the meta positions, which really comes into play when you look at the resonance contributors. You'd be putting the positive charge at the position where the chlorine is. Okay. Well, what would we classify that as then? If one of my resonance contributors in my intermediate looked like this, is that primary, secondary, tertiary?
Secondary, tertiary.
Officially secondary, but according to our broader definition, that kind of classifies as tertiary. Because when we're using that, we're really trying to classify the stability of the carbocation. Is that carbocation reasonably stable? Yeah, it's kind of a tertiary carbocation. Because of that increased stability, I direct para and ortho. The para-ortho argument really comes from looking at the intermediates. The activator-deactivator now becomes the interesting or the question. Okay, is the chlorine willing to donate electrons into the ring? No. Why not? Okay, so we could go, it doesn't want to share full octet. Even if it has its full octet, it's still going to be able to do that. It doesn't invalidate its octet to share the electrons. This argument comes up with what Corey said already. Chlorine is big. Does it have orbital overlap with the ring to facilitate electron donation? No. Which then means no resonance, and what follows resonance?
Stabilization. Or, sorry.
An inductive effect. Chlorine is more electronegative than our hydrogen. The electronegativity effect contributes or dominates now, and we see a deactivating effect on the ring. Our halogens sit right smack dab pretty much in the middle. They will direct the para-ortho positions, but they deactivate the ring and prevent it from continuing, or slow it down at least. For those of you going, God, finally another freaking exception. Our halogens are the only weird exception. Okay, with our EAS is lovely. Okay, what we just discussed sets everything up.
You can still get a product.
You still get a product.
Para
Yep.
Or no, the
Yep.
para. Okay.
Yields and time to get to said product are something that we typically don't evaluate in the lecture, so don't panic on that end. We still have a product potential. Okay? So, with that, we've got all our fun resonance with those answers. We could then address some of the other issues. Our Friedel-Crafts alkylation, remember, required an active nucleophile. Okay? Because of that, if I use a deactivated ring, say like the chlorobenzene, I cannot add an alkyl group through the Friedel-Crafts alkylation. Okay, so let's actually not put that there, and I'm going to redraw it again anyway. So how could I possibly get, say, this result? How can I get a CH3 on there then?
It activates those spots.
But the chlorine is a deactivator, and the Friedel-Crafts reaction or Friedyl-Crafts alkylation requires an active nucleophile.
So you don't do a Friedyl-Crafts.
So I can't do the Friedyl-Crafts alkylation.
But you do something else, right?
Okay, what else do I do?
Remove the hydrogen.
What's that?
Did you remove the hydrogen?
Remove what hydrogen? From the benzene? Is that what you're trying to say?
Yeah.
Okay, yes, you have to do that. That's EAS. That's going to have to happen. The hydrogen's not acidic. You can't just remove it from the structure.
Do you have an acid?
Still,
That's fine.
the hydrogen's not basic, so adding an acid doesn't help. Okay, sodium borohydride. Sodium borohydride will reduce carbonyls. There's an interesting thought with that. That could reduce carbonyls, but there's no carbonyl there. Okay? And we just said the Friedyl-Crafts alkylation doesn't work, so let's just get rid of that altogether because that's not going to help us. Sodium borohydride would reduce a carbonyl away, but there's not a carbonyl attached to our structure yet.
Let's add
How do you add the carbonyl?
Friedyl-Crafts, but we can't do that.
Careful. Friedel-Crafts is not a universal term.
Well, then, CL.
What you are referring to is the Friedel-Crafts acylation, which is not conveniently erased from our screen. The acylation does work. The alkylation does not. The acylation works because we form our resonance stabilized carbocation. So the acylation generates a more stable electrophile. It can react with a deactivated ring because it exists for long enough that even the deactivated ring can potentially react. Okay. So let's say we went through and did that. What would we get? Okay, and let's just say it goes to the ortho. Yes, it would officially go to the para, but let's say we eliminate that issue. And we get it going to the ortho position. Could try Troy's option, reduce the carbonyl with sodium borohydride. I still have too many carbons. How could I get rid of a carbon? No.
Add water.
No.
OH.
No. 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 Interesting enough, the I2 would work. Yeah, I would accept that. Could do the I2 and OH minus. That would do that because that is officially a methyl ketone, so that could work to do that. There's another one that we actually talked about. We talked about on Tuesday. Monday. Permanganate. Permanganate will oxidize and cleave that all off and leave us with the benzoic acid. Okay? But that's still not a methyl group. How can I go from the carboxylic acid to the methyl group? What's that? Now I can try and go through some reductions. Okay? And yes, that could be problematic, but I think we might be able to get away with that if we did really strong hydrogen and platinum or palladium. Maybe. The carboxylic acid gets a little bit trickier to reduce down.
Well, you could use the HCl and do that.
Yeah.
Or to get rid of the carbonyl group,
Or we can make it easier.
then you're still left with the alcohol.
That's not fun.
Yeah, sometimes it is. How do I do that? HCl on our iron or zinc or freaking a billion different things. Tin doesn't, actually. tin will only react the nitro. Yeah.
That's tricky.
Yes. Okay. So if we have a deactivated ring, we can still alkylate, but we're alkylating indirectly. We're putting on the acyl group, and then we can reduce the carbonyl away. And that's what our HCl and iron does. Yes, Ree, what's up?
But now we have,
I added an extra carbon.
yeah. Oh,
So now it's straightforward. That's really what I wanted, was it just be straightforward. Okay. Nifty. Okay. The other fun thing is our nitrogen. Remember, we said our nitrogen could act as a base. What else do nitrogens act as? Nucleophiles. What was aluminum trichloride? An electrophile. What happens if we have aniline? The aniline will react with the aluminum trichloride to form that positive nitrogen, which then means no Friedel-Crafts reactions or alkylations are again possible. Okay, so we again have to watch out for that. So nitrogens will kind of get in the way all the time. What's happening here? What would we expect as our product now? Okay, I agree. Let's put it at the para position because that's the most likely. Put a CH3, right?
yep.
Right? Except what do I say the problem is? Polysubstitution. What do you end up getting?
More than you get both.
You also get the CH3s up here. Why? Why is it now going everywhere?
Because the oxygen can keep donating electrons, or
But why is putting a single one on changing how oxygen donates electrons?
it's not maybe. Because
You're right, it's not.
It's CH3 because it's still an activator.
CH3 is also an activator. So if we compare our starting material, the anisole, to our methyl anisole, which one is more activated? The methyl anisole. So now given the option, which one reacts? The methyl anisole. This is very similar to the question on exam 3 with the ester and our Grignard reagent. The ester reacts with the Grignard reagent to make a ketone. Ketones are more reactive than esters. The Grignard reacts with a ketone. Same idea is happening here. The very first product we produce is more reactive than our starting material, so it reacts with the reagent instead of our starting material. Okay, so the Friedel-Crafts reactions have a lot of potential issues popping up with them. What happens if we'd, instead of alkylating it, okay, so let's say we did, again, with 2 carbons, would we expect polyacylation?
No,
Why not?
nothing yet.
The acyl group deactivates. So the anisole may be activating, but as soon as I make the product, it is now less active than the starting material. I won't get polysubstitution. I'm actually slowing the reaction by producing product. Kind of neat. So the Friedel-Crafts acylation tends to be the more common reagent used because it doesn't have limitations on the nucleophile and it doesn't get held up by or affected by polysubstitutions. Okay? Yeah. Oh, there's our weird aromatic halogens. Yeah, I thought that was fun too. What was our weird aromatic halogens? Any of our halogens have more electrons than hydrogen, so they can be classified in the kind of activating para-ortho category, but they are also electron withdrawing due to their electronegativities, and their lack of an ability to donate electrons, because they're so big, okay, makes them deactivators and meta-directors. Because they straddle that border, what we end up seeing is a blend of them. They become para-ortho directors and deactivators. Okay? Just kind of our last minute summary on that. So multiple substituents. Okay? Sorry for the nitro being sideways. I just wanted it moved and didn't want to redraw it, so I copied and pasted and then rotated. Okay. Where would we expect the bromine to go in the first reaction?
Ortho to the CH3.
Why are you saying para?
Isn't CH3 active?
CH3 is an activator, and it directs para and ortho. So we could suggest it would be going to the para position. Come on, pen. CH3. Okay, what's the issue that you had with that, Tyler?
The issue is that you're in the ortho position to the NO2, and we found we didn't get that at all.
Interesting. The NO2 directs to the meta position.
Well, one's an activator and one's a deactivator.
Okay. Does that matter? Yes. Absolutely it matters. Okay.
I didn't like the proximity to the NO2, so I didn't know.
Okay. So if you don't like that, then we could have just as easily done something like this. Does that solve the nitro directing to the meta position? No.
No.
Okay.
So let's go between.
Well, even if it went over there, it still doesn't solve the nitro going to the meta position. So now the question becomes, should the bromine be directed to the meta position because of the nitro, or the para or ortho positions because of the CH3?
Meta position because nitrogen is charged.
What must our ring act as? A nucleophile. If it does not act as a nucleophile because there's something withdrawing, what happens to the speed of the reaction? Slows down, doesn't happen.
So then this would have to go to.
Doesn't happen.
So one thing prevents the reaction from happening, the other thing allows the reaction to happen. Which one do you think is going to dominate? The activator. The activator dominates in your results. We end up seeing our purple results, okay, or sorry, our red result, with potentially the para, or sorry, the ortho to the CH3 being our
So even
other
though
contributor.
the charge on the nitrogen, it gets dominated by the non-charged carbon.
So you are referencing the charge on that carbon, or sorry, on the nitrogen, but you are referencing it according to the intermediates formed. Do you put a positive charge at that position?
Oh, I see what you're saying. At that carbon, you mean?
Yeah.
No, you don't.
You wouldn't. So you don't need to worry about that. Okay. There is officially a third product. Which of these would be the least likely to form, which is the easier answer, or easiest answer? The last one should be the hardest to form because sterics. Between the top two, it's a hard decision. I would probably still push para. Okay. Para to the methyl. I'm basing it off of the activator. Okay. How about the bottom one? The ortho. Which ortho?
So, the bottom.
To the activator, right?
Yeah.
They're both activating, aren't they?
Oops.
So what happened?
Oh shoot, they're both activators.
So all four are ortho for both of them?
So which location do we place the nitro?
Well, when you press the nitro, you have a deactivator as a ring option.
So we're still only doing one substitution, so I don't care about that. Red or purple?
Both.
Both is kind of a fair answer, but let's pick the majority. Which one is our majority?
Probably the red one.
Why purple?
Taking steroids. Purple
When we went back and looked at the CH3 versus the nitro, we said the CH3 dominated because it was an activator, right? Or said in slightly less strict terms, it was a stronger electron donating group than the nitro group. If we moved the OH versus the CH3, which product should form? The red or the purple? The purple, because OH is a stronger activator than the methyl. Our substitution is going to go based off of the strongest activator, wherever that activator may be. It's going to dictate the substitution pattern. Because it's the one that's driving, making the nucleophile more nucleophilic. That's how our reaction sets up. And it could have just as easily gone to the other side, but if it went to the other side, same product, we just flipped it over. Jiminy. It's a good thing it's getting close to the end of the semester. Put someone's eye out. So activator trumps deactivator, stronger activator trumps weaker. So said probably a better way in just one rule, pick the strongest activator. That's the one that dictates. And with that, we'll have to end